Welcome back to another lecture from organic chemistry. I hope you had a great weekend and you're full of energy to start another week from the semester. In this chapter, we're going to go through stereoisomers. The main purpose of this chapter is to figure first, do we have a stereocenter? Okay, do we have chirality? Now that we have chirality, do we have enantiomers or diastereomers? And we're going to go after those one by one. So let's start. And the first thing that we need to know, are we dealing with constitutional isomers or stereoisomers? How do I differentiate these two from each other? Let's start with a really simple example. The simple example is going to be, for example, this one. Okay. So I have oxygen. Let's say I have oxygen, and that oxygen, I'm going to attach it to two carbons. And those two carbons need to be octet, so I'm going to have CH3, CH3. Okay, what's the formula for it? The formula for it is C2H6 and O just 1. This is ether. It's a dimethyl ether. Okay, you can draw another structure by using the same formula. And in that case, we say you have a carbon attached to another carbon, and that carbon is attached to oxygen. And let's attach hydrogen to oxygen. Next, we're going to put enough hydrogen in each carbon until we make them octet. Okay, now all carbons are octet, oxygen is octet. What's the formula for it? We have two carbons, we have 6 hydrogen, and again 1 oxygen. What's the relationship between these two? The top one is ether. Okay, the second one is alcohol, is ethanol. We have two compounds that they have exactly same formula. So their molecular formula is the same, okay? The only difference between them is connectivity. So the only difference between them is the connectivity. And what do I mean by the connectivity? For example, follow oxygen. Oxygen used to be between two carbons. Now oxygen is here. It's between hydrogen and 1 carbon. And so clearly we change the connectivity at least about oxygen. If you change the connectivity, if you break bonds and you form new bonds, and you get a new molecule, we say you got a constitutional isomer, okay? Constitutional isomer. So the constitutional isomers are isomers that they have different connectivity, but the formula still is the same. Now, when it comes to stereoisomers, the connectivity is the same. The connectivity is the same. So what's the difference between them? The difference between them, their structures in space, or the 3D, okay? 3D structure, or sometimes we call it spatial. Okay, spatial structures are different. Okay, so the connectivity is the same. The only difference between them, it will be technically their structure in a space. My right hand is pointing to the right side now, okay? And if you get mirror image of me, if I stand in front of the mirror, I will see my left hand is, pointing to the other direction, okay? So I'm raising my right hand right now. It's up, okay? And inside the mirror, my left hand, it will be up. And in that case, we say we have a mirror image, or like the difference between them. It's just technically their 3D structures are different. Okay. We have we said when it comes to rings or double bonds, we say the structure will be locked. What does it mean? It means there will be no rotation around the carbon-carbon bond. So that structure is going to be locked. And what do we have here? We have a cis structure. Okay. Why is cis structure? Because I have 2 methyl group. They are pointing up and they are in the same direction. Okay. Only thing I care about that they are in the same direction. Because they are in the same direction, it will be cis. Okay. And I have a ring. Ring is made of 6 carbon. I see the same ring on the other side, same connectivity. Again, same connectivity, only difference between them. This one is up, and the second methyl is down. Okay. And in that case, we say we have trans isomer. Well, the first one was cis isomer. Okay. Okay, so I have cis isomer and trans isomer. What's the relationship between cis and trans? The relationship between them, we say these two are stereo isomers. What does it mean? It means they have exactly same chemical formula, same connectivity. The only difference between them, the way they are oriented, or the way they, like connected actually to the molecule in a space is different. Okay, in a space, I'm saying in a space is different. And one of them, two methyls pointing same direction, another one, and they are opposite. So the direction is different. Well, on first carbon, you have a methyl, and the second carbon also you have a methyl. First carbon, you have a methyl, and the second one, again, you have a methyl. So the connectivity is the same, only the direction is different. Another one, we have a cis and trans isomer. Or you can say the first one is Z, okay, because they are in the same direction. And the second one, it will be E, because they are cross of each other. When I say cross of each other, I'm talking about those, okay, those substituents. And what's the relationship between these two? Again, we're dealing with stereoisomers. Okay. Always, cis and trans will be stereoisomers. Always. Why? Because cis and trans will have different, technically, shape. Okay, listen carefully. They have different shape. Why different shape? Because the methyls and cis, they will pointing up or same direction. Then trans, they will be opposite. Okay, and that's the reason we call them, stereoisomers. Okay, what do we have here? Let's assign whether it's a cis or trans or none of them. Okay, the first one, I have one substituent here. Where is the second substituent? Is there. Okay, that's going to be my second substituent. So you start from here. Okay, they are on the same side. This is going to be cis. Okay, next one. I have this OH is pointing up. So I'm going to say the OH in axial position and is pointing up. And the second one, it will be equatorial. How do I know it is equatorial? Because you will have axial position there and hydrogen is taking it. So OH, it will be in equatorial, and it's pointing up. Now you look to this two. Both of them are pointing to the same direction because they are pointing same direction. This is going to be cis again. Okay. How about next one? We have one substituent here, and the second substituent is there. And what else? We have hydrogen here and hydrogen there. Okay, as you see, the hydrogens are across of each other. And or you can say those two are across of each other. So this one, it will be trans. Or you can say it's going to be E. Trans or E. Okay. And how about this? Okay. We have two substituents that they are identical. Okay, two substituents are identical. And here we have hydrogen and methyl. Okay, you can say cis or trans. Why? Because let's say you decided to go with this one. Okay, and you want to compare it with another one. Okay, well, like if I compare it with this one, it will be cis. But if I compare it with that one, it will be trans. So in that case, it's going to be none. Okay, none of them. And how about this? We have one OH in axial position and it's pointing up. The second one, it will be axial again, but it's pointing down. Okay. You look to cis and trans. Sorry, my bad. Up and down, up and down. One is up and the second one is down. So this is going to be trans. Okay, now that you know how to figure whether it's a cis or trans, we're going to use this one to talk about whether we have stereoisomers or not. it says, tell me whether we have constitutional isomers or stereoisomers, or maybe we have identical. Okay, maybe we have identical isomers. Okay, and so let's see. And I'm gonna start with this structure. Okay, this one. And let's look to the left side. What do we have? We have this group that is identical to that group. Okay. Am I dealing with any isomerization here? No, not really. I don't have cis or trans. Okay, so these two are gonna be identical. Okay, those two are identical. What else? Okay, let's check here. We have this double bond. Okay, and double bond, if you looked at it, you have one substituent is there and the second substituent is here. You have one substituent here, but the second substituent is in the same direction. Okay, so the first one is going to be, you can say, is a trans or E, or the second one will be cis, or you can say Z. So in that case, we do have stereoisomers. Okay, next. Here, the connectivity clearly is different. Look to oxygen. In one case, oxygen is connected to carbon through a single bond. On the right side is a double bond. So connectivity is different. But before I say those two are constitutional, I need to check the formula. Okay, the first one, we have 4 carbons. Next, we have 1, 2, 3, 4, and then each carbon is going to have 2 hydrogen attached to it. So technically we have 8 of them, and oxygen just 1. And how about here? 1, 2, 3, 4. So we have 4 carbon, hydrogen. And start with 3 here, 2 there. That's going to be 5. And 3 there, it will be 8. So hydrogen, we have 8 of them. How about oxygen? Just 1. In that case, I'm going to say I'm dealing with a constitutional isomer. Okay. How about this two? Okay. This two, we have one is up. Okay. And that one also is up. So what do we have here? This is going to be cis. Okay. Next one, this one is up, and that one is down. So I'm dealing with a trans. And because it's a trans, I'm going to say I'm dealing with stereoisomers. So these two are stereoisomers. Okay, I need a space for those two, so I'm going to write it here. Stereoisomers. Okay. Here I have a structure that it has OH in axial position. Okay, so I'm going to say axial, and what else is pointing up. And this one, it will be in equatorial. And is pointing up. Okay, what should we call this? Okay, I want you to give it a try, and I will mention this one next lecture. So try to answer this one, whether it's constitutional, stereoisomers, or you're dealing with identical structure. Thank you very much, and I will